Good day, everyone. I'm Olusola Olajide. I'm a PhD candidate from Concordia University and University of Ottawa. Today, I'll be giving a presentation on our ongoing PhD research, which is on the multi-level assessment of the influence of moisture and temperature in alkali silica reaction-induced expansion and deterioration. My supervisors are Dr. Mitchell and Dr. Leandro Sanchez. Now, alkali silica reaction, ASR, is a very common form of alkali-gate reactions. The ASR is a mechanism caused. Oh, okay. Thank you. The ASR is a mechanism caused by the reaction between poorly crystallized siliceous phases in aggregates with alkalis from cement. And in the presence of sufficient amount of moisture, an expansive gel is formed, which can expand and cause cracking in affected concrete. This mechanism has been known to cause severe durability challenges in affected concrete. Now, moisture and temperature has been known to be driving factors for this reaction, and a moisture threshold of 80% relative humidity has been deemed required to initiate or sustain the reaction. According to the work carried out by Deterioration et al. In 2018, the increase in moisture and temperature can significantly enhance the development of this reaction. However, it is worth noting that these studies, along with several other studies on this subject matter, has been limited to the use of the external relative humidity without considering the internal moisture, which is more critical for the sustenance and initiation of this reaction. Furthermore, most of these studies only consider expansion attained over time, disregarding the influence of this expansion on internal distress and even associated mechanical property losses. Now, this research is focused on the use of the multi-level assessment techniques, which involves the damage rating index to assess the impact of expansion on internal distress, and the use of the direct shear test and stiffened damage test to assess the associated deterioration from ASR. So today we won't be discussing the SDT due to time constraint. The damage rating index is a spectrographic-based semi-quantitative tools which can be used to assess ASR damage in concrete. Basically, it's carried out using the stereo microscope or 15 to 16 times magnification, and crack features, as highlighted in this table, can be counted through the microscope, and these are multiplied by weighting factor, as highlighted in this table. Now, a DRI number is obtained by taking the sum of all these weighted petrographic features and normalized to 100 centimeters squared. Typically, the increase in the DRI number results in the increase in the ASR-induced deterioration. For the mechanical property losses, aggregates are known to produce frictional resistance of cracks to sliding. And since alkali silica reaction is a deterioration mechanism in aggregates, the direct shear test has proven promising in assessing the influence of ASR damage in affected concrete. Now, according to the work done by Souza et al. In 2019, they concluded that alkali silica reaction can significantly reduce shear strength, especially at low to moderate expansion levels. Now, for the objectives of this research, the first involved is to monitor the internal and external moisture in affected concretes and how it affects alkali silica reaction development. And the second, third, and fourth objectives are mainly to monitor or to assess the development of alkali silica reaction, the influence of this expansion on internal distress, and the associated mechanical property losses using the direct shear test. In order to achieve the first objective of this research, a framework was designed, as shown, to monitor the internal and external moisture in affected concrete. Basically, it involves the use of high-burden sensors, which are inserted in the middle of the concrete samples, as well as in the storage bucket, to monitor the internal and external relative humidity over time. For the second, third, and fourth objectives, an experimental program was designed, which involves the use of a highly reactive aggregate, SPACs, as reference aggregates, to prepare concrete specimens according to the ASTM C1293 with an alkali level of 1.25% sodium oxide equivalent. These samples were stored at 3 different temperatures, as highlighted here, as well as 5 different relative humidity. Now, the DRI test and the shear strength test were performed on these samples. And the tests were done after 6 and 12 months of exposure for samples stored at 21 and 38 degrees Celsius, while for 60 degrees Celsius were carried out at 3 and 6 month exposure. Now, here are the results of the internal and external moisture carried out for a period of 365 days at relative humidity from 62% and 100% average. Basically, we realized that the internal moisture, which is represented in orange, either increases or reduces to equilibrate with the external relative humidity. However, the rate of equilibration is dependent on the internal moisture. As shown, the relative humidity, the internal relative humidity at 90 and 100% equilibrates faster as compared to those stored at 82 degrees Celsius. Relative humidity. However, the 62% and 82% relative humidity fail to equilibrate throughout the duration of the experiment. So this result shows that even at a low ambient relative humidity, the internal moisture in concrete could be sufficient enough to initiate or sustain alkali silica reaction. Now, here is the kinetics of the reaction using sparks at 21 degrees Celsius at relative humidity between 62% and 100%. As shown, the kinetics of the reaction increases as the relative humidity increases, and the ultimate expansion was attained at 100% relative humidity, which is about 0.11%. Now, to compare the kinetics at 21 and 38 degrees Celsius, using similar moisture conditions after 365 days, the kinetics of the reaction even extended or even improved further, and the ultimate expansion at 100% relative humidity is about 0.22%, which is like double what was experienced as 21 degrees Celsius. Now, finally, using the same aggregate, but for 188 days and similar relative humidity conditions, an interesting result was obtained at 90% and 100% relative humidity. The 90% has an expansion almost higher than 100% relative humidity, which is as a result of alkali leaching at high temperature. Now, to give a correlation of these results at these 3 different temperatures, we realized that the highest ultimate expansion was attained at 38 degrees Celsius, and at low relative humidity, especially at 62, 75, and 82%, we experience a high drying shrinkage. Now, we exposed some samples to damage rating index to assess the influence of this expansion on internal distress. Now, for samples stored at 21 degrees Celsius, after 6 months of exposure, we realized that we have a similar DRI number across these relative humidity conditions. However, the sample stored at high moisture condition attained a significant damage ASR petrography features. However, those stored at 62%, 75%, and 82% experience almost similar DRI number, which is as a result of the drying shrinkage, which caused a lot of CCP, crack in cement paste. Nevertheless, the OCA, which constitutes the open cracks in aggregate, which is one of the symptoms of alkali silica reaction, increases as the relative humidity condition increases. Now, comparing these results for those stored at 38 degrees Celsius, similar trend was observed at high moisture conditions as some ASR features were experienced over time. However, for samples stored at 62, 75, and 82%, they were quite close, which represent the similar deformation that was obtained in the expansion result, that is shrinkage versus expansion, which is about 0.2% and negative 0.2%. Now, at 60 degrees Celsius, the ASR-Induced pictures were more pronounced as the relative humidity condition increases. Now, at the end of the test, we also tested some samples using DRI. Now, at 21 degrees Celsius after 12 months of exposure, significant increase in the cracks in the aggregate was experienced as compared to those stored at 60 degrees after 6 months. Actually, more than 40% increase in OCA was experienced even at low relative humidity conditions as compared to those stored at 6 months. This shows that even at a very low moisture conditions, Alkali Silica reaction is ongoing. Now, at 38 degrees Celsius after similar exposure or duration, we also experience cracks in gel, cracks with gel, even at low moisture conditions. So comparing those stored at 38 and 21 degrees Celsius, we can see the significant difference due to temperature. Now, finally, at 60 degrees Celsius, the DRI number, the sample stored at 90% and 100% relative humidity is having almost similar DRI number, which has something to do with the expansion we had here, which is almost the same between 90 and 100% relative humidity. Now, we decided to do the direct shear test to determine the influence of this expansion and internal distress or mechanical property losses. And here is the reduction in direct shear at, for sample stored at 21 degrees Celsius after 6 and 12 months of exposure. And according to this plot, the reduction in direct shear increases as the relative humidity increases, which coincides with the increase in expansion. At 38 degrees Celsius, using the same aggregate and for similar exposure condition and duration, the similar trend was observed as compared to those stored at 21 degrees Celsius. However, it is worth noting that at low moisture condition of 62% and 75% relative humidity, despite the net shrinkage that was obtained or that was recorded at these low moisture levels, we have attained more than 15% loss in shear, direct shear, which shows that despite the shrinkage that was reported, Alkali Silica reaction is currently ongoing. However, the drying shrinkage is the leading mechanism at this point. Finally, at 60 degrees Celsius, the direct shear loss, especially at 90 and 100%, replicate what we had in the expansion and DIY results. Now, we decided to plot a graph that can be used to relate a mechanical reduction with our DRI features. As we know, the cracks in the aggregate will play a major role in aggregate interlocks, and in this case, the cracks with or without gel will be critical in our assessment. So this plot has the direct shear losses in the vertical axis and the cracks in the aggregates with or without gel in the horizontal axis at 21 and 38 degrees Celsius after 6 and 12 months of exposure. And according to this plot, we realize that the increase in the cracks in the aggregates correspond to the increase in the loss in the shear strength. Now, to conclude, first, we realize that the internal moisture in concretes is actually higher than the external moisture, especially at low moisture condition. So what does this tell us? It says even at low ambient conditions, Alkali Silica reaction can actually be initiated or sustained. Secondly, considering the expansion results we have, we realize that the initiation of this reaction can be dependent on the temperature. And we are doing some other works on using the different aggregates of different level of reactivity levels so as to further confirm the moisture threshold needed for this reaction. Thirdly, going by the expansion result we also presented today, we realize that there's a lot of drying shrinkage at low moisture levels. So we're also working on how to decouple drying shrinkage from the net expansion at low moisture conditions so as to determine the actual expansion that can be attained at low moisture levels. Finally, there exists a correlation between the petrography features and mechanical property losses. So using the multi-level assessment techniques will be efficient in monitoring in assessing the influence of moisture and temperature on ASRs induced deterioration, especially at low moisture levels. Merci, thank you. I would love to entertain questions now if there are any.